Hi, welcome to the Signal Path. In this episode, I have a world-exclusive product review for you guys. I've had this unit for some time under NDA, but now that it's officially announced, I can actually show you guys and show you what it can do. I'm talking about the Tektronix RSA306 real-time spectrum analyzer. This is a 9 kHz to 6.2 GHz spectrum analyzer, and as you've guessed by its size, this is a USB-based unit. Now, making a USB-based unit is very difficult because A, you have to make sure that it fits in something that's reasonably sized, but also you don't want to make too many compromises. And the software better be absolutely amazing in order to be able to replace a dedicated spectrum analyzer that will sit on your bench. And I have to tell you, Tektronix has taken some really interesting marketing directions for this product, and I'll show you. And they've made some big changes on some of the product prices, which is amazing, especially if you cannot afford a 6.2 GHz spectrum analyzer normally, because this is priced really interesting, and I'll show you that in the slides. And we're going to take a really close look at it. We're going to push it to its limits, do some experiments with it, tell you exactly what its weaknesses are and what its strengths are, so you can make a decision whether this will suit your application. But this is absolutely ideal for educational as well as for field use, and I'll show you some of those examples as well. Well, I'm sure you're eager to see it, so let's get started. So let's take a closer look at the unit. Here it is. Here's the front of it. It's the Tektronix RSA306 real-time spectrum analyzer from 9 kHz to 6.2 GHz. So it's built really solid. The whole case is supposed to be shock resistant, again obviously because it's meant for field use. The rubber that's on the outside is nice and has a good grip to it. These ridges really help for you to hold on to so you don't drop it when you're using it outside. And you can see at the back it's got, it's upside down. At the back you got the nice Tektronix logo. Again, I like the build quality of this thing. It doesn't weigh very much. It's essentially the size of a book, and it weighs maybe just a little bit more than that. If I were to compare it, for example, to the Fluke 289, it's actually significantly smaller, and it weighs much less than this, especially when the batteries are installed. So it's very portable, intended for, of course, portable usage. And at the back, you can see that it has a lock. And you may ask, why have they included the lock? Because they're also considering this for educational use, in the laboratories around different schools. So if you want to put one of these on each bench, you want to be able to lock it down so that the students don't pick it up and walk around with it, or it gets lost or stolen. And you can see that it says it's assembled in the United States from US and foreign components, which is nice because it means it's manufactured here in the United States. It's nice when test equipment are manufactured locally. I always support that. And you can see that in the front of it, it actually comes with a protected Type N connector for the RF input. And Type N connector is the industry standard, especially for field use and for instruments that are usually below 26.5 GHz. This is common, and it comes with this protective rubber case which is connected to the main body so that you don't lose it, so you can close it when you're not, when it's not being used, when it's transported, so to protect the connector from stuff getting into it. And the Type N connector also helps, especially in educational environments where people may not be familiar with how to take care of really sensitive RF connectors, and this is a much more rugged type of connector. And you can see that it says that it can take up to plus or minus 40 volt DC, so it's AC coupled internally, just like the others typically on the spectrum analyzer starting from 9 kHz, but it can only take 20 dBm and not 30 dBm, so it's 100 milliwatt and not 1 watt. And that means that they probably saved on the area that would be consumed by an extra stage of attenuation in order to be able to absorb a 30 dBm of power. Remember, between 30 dBm to 20 dBm, that's 10 times the power. So, it can take much less. So you have to be a little bit more careful. If you're going to use this for, something that you're thinking that a lot of power might come inside, it's good to have an attenuator with you. But plus 20 dBm is a lot of power, and it's used for a whole variety of applications. It also has a reference input, a 10 MHz reference input with a maximum of 10 dBm. It means that you can lock this instrument to another instrument, but it doesn't provide you with a reference output, so you can't lock another instrument to this, which is okay. And for most part, you usually want to lock this one to another much more stable, perhaps, reference 10 MHz input, which is nice that this accepts that. It also has a trigger input, which is a TTL type input, and has a 10 kilo ohm input impedance. Very useful also when you're looking for a particular trigger event that may be happening on the spectrum, so you can tell the software to look for the trigger before it actually records or captures a particular spectrum waveform. Again, very useful. It takes a USB 3.0 connector, and it only works with USB 3.0, and it comes with a cable, of course, and there's a little bit of an LED here that tells you different things like status. It blinks red and green when the connection is established and the data is being transferred. But what you don't see on all of this is, of course, a power cord. So this doesn't need any external DC power. which is a huge advantage. All you need to do is you need to connect it to a USB 3.0, and that's why it needs a USB 3.0 connection for a couple of reasons. First of all, it gets all of its power from USB 3.0, which is rated up to just under 5 watts. So this thing consumes less than 5 watts. And also it utilizes about 80% of the maximum throughput of USB 3, which is very impressive, meaning that you get a lot of data transferring from this to your computer. I think it utilizes, they mentioned something around the line of 300 megabytes per second is the data rate that comes out of this. So it's pretty amazing that you can get, and this is very important. If you're going to make a USB unit like this, you better have a really good interface to your software so that the interface is seamless. You don't want to be limited by the connection from this to the instrument when you want to capture and display data. And as we will see, when I turn it down, they've done a really good job making sure that this is not the limitation, the interface is not the limitation to the computer. Very important, impressive design, so the whole thing consumes less than 5 watts and it does everything within that. So let's take a look at a couple of slides, and I want to talk about the pricing of this and how the software pricing is configured, because it's really important. They've changed the policy on that and it's good to know, and then we'll start our experiments. So here's a nice slide from Tektronix showing the dimension of the unit, which I don't think I mentioned. It's 7.5 by 5 by 1.2 inches. Again, quite nice and portable. So now at this point you must be asking, so how much does something like this is going to cost? Well, Tektronix has set the price at $3,490, which is a really good deal for two main reasons. Well, we'll get to those two reasons in just a second. So it gives us a dynamic range of from minus 160 dBm to plus 20 dBm, which is quite a large dynamic range, allowing you to capture really small signals all the way, and of course signals as large as 20 dBm. And if you have an external attenuator, of course you can measure above that. The accuracy of the internal reference is 1 part per million. But of course, if you overwrite that with an external reference, then your accuracy will be depending on the external reference. And I believe it has a phase noise of about 85 dBc per hertz at a 100 kilohertz offset, which is okay. It's not really high, but for a portable unit like this, it doesn't seem to be causing any trouble, especially for capturing something like a 256 QAM or FDM, which we will take a look at. It seems to do that quite well. And it weighs only about 0.6 kilogram. But what really distinguishes this unit from other either portable spectrum analyzers or even bench spectrum analyzers, it has an analysis and capture window of 40 megahertz, which means that you can do vector analysis, full vector analysis within a 40 megahertz bandwidth anywhere between the 9 kilohertz to 6.2 gigahertz capture range, RF capture range of the unit itself. This is a really powerful tool, meaning that you can do very fancy analysis on a 40 megahertz signal, which all of the different protocols that operate between these two ranges, you're going to be able to capture and analyze. Another thing it does, which is really impressive, is that it has a minimum signal duration 100 microsecond analysis. This means that if you have an event that is at least 100 microseconds long, you have 100% chance of intercepting that event within the 40 megahertz bandwidth that you're capturing. This is equivalent to the waveform update rate of an oscilloscope. For example, why do we want to have high update waveforms from an oscilloscope? The reason is because we want to capture really rare events that don't happen very often without having to wait for a very long time, so that by chance we eventually hit them. This is an equivalent idea in a spectrum analyzer. For 100 microseconds, this instrument gives you at least 10,000 waveform updates per second. That way it makes sure that you can capture something that's 10,000 and something that's 100 microseconds duration within a spectrum. This is a DPX technology from Tektronix, equivalent to the DPO technology, which gives you this color grading, which corresponds to how frequently an event is actually happening in the frequency domain. You can get a similar thing in a time domain. We've seen that. This is an equivalent of that in the frequency domain. And if you have this, then you can make sure that you capture anything that's 100 microseconds, at least in duration, with 100% probability. If your event is less than 100 microseconds in duration, you will not catch it with 100% probability right away. It will take some longer amount of time for you to catch that event, but you will eventually catch it. But this is really important when you're using it in a field and looking for an intermittent interference that comes and goes without having to spend a long time. Particularly, it's impressive because all of that 10,000 waveform update per second, all the communication is all done through USB 3.0. So they've set a standard, a minimum requirements or so for your PC. Of course, this is an aggressive number they have given. I've tested it on my Surface and it seems to be just fine, which of course doesn't meet this. But if you have such a specification, then there's a 100% chance for you to be able to intercept that signal that you're looking for. So the second reason why this is such a good deal is because what Tektronix has done, which was a big surprise to me, is that they have now made their Signal View PC software free. This is a huge deal. This did not used to be free. It used to cost quite a bit of money. And what they've done is that they have taken 17 basic measurements of the Signal View PC software and made it free and available with the purchase of course, of the Tektronix spectrum analyzer. So you can download and play with all of these functions, which are all the main functions you would expect to see from a spectrum analyzer. You get the DPX technology in there, the spectrograph is in there, and a whole bunch of advanced measurements to help you debug and analyze and characterize particular circuits. And what they've also done is that they have significantly reduced the price of all the other options that are available from Signal View, and I'll show you the prices in just a moment. Here we go. This is the prices that they have set. So you can see the basic software unit, the SVE option, is now completely free. $0, so they get all of these things with the Signal View, and all the other different options have been dramatically reduced in price. So the general VSA has gone from $6,700 to only $990. The VSA is the vector signal analysis, and all the other options have been significantly reduced in price. Now actually affordable even for hobbyists. Really, at this price, now you can do signal demodulation and analysis for $990 plus the cost of the spectrum analyzer itself, all the way up to 6.2 gigahertz. This would have been unheard of, 6 or 8 months or a year ago. I've never seen something with so many functionalities being made available, and this is really what distinguishes this unit. This is backed by Tektronix with their software that's been developing for years, and of course with their hardware, making this an amazing, amazing deal. Here's a quick overview of what to expect to see on the market. So these are typical spectrum analyzers that you see. For example, the Rygo 7.5 gigahertz, $8,000 is the lowest price spectrum analyzer in this range, which does not offer digital analysis even at that price. But here you have the Tektronix RSA306 at $3,500, offering vector analysis as well as up to 6.2 gigahertz of bandwidth. There's a whole bunch of other low-cost signal analyzers on the market, but again, what distinguishes a USB-based instrument is of course the software. And now having Signal View free to interface with it really can't beat that. I'm very curious how other manufacturers are going to react to this approach by Tektronix. This is quite an aggressive pricing scheme for such a product. Okay, so let's do some really basic tests with the RSA306. Here I have it connected directly to the RF output of my synthesizer. This is an Azure E4432B, which is capable of doing constellations as well as RF tones and two-tones and multi-tones and so on, because it has a built-in ARP, which is going to be really useful in characterizing and understanding the strengths and the limitations of this USB spectrum analyzer. And so when I was talking to the engineers at Tektronix about this, they told me that the spurious free dynamic range, the SFDR of this unit, was only rated as 55 dB. And I was really surprised because the analog to digital converter that's inside this, which does the analysis at a 40 megahertz window, that is a 14-bit converter. So the SFDR should be significantly better than 55. Then it turns out actually they're reporting the absolute worst case of the SFDR. There appears to be some RF isolation limitation inside this issue, which prevents from all the spurious tones that are internally generated not to leak to the output, and that is caught by the ADC and then displayed. And that limitation is what they're reporting. So they're actually being conservative, because during most of the frequency range of this, you're going to get a much better SFDR than the number they're reporting. But nonetheless, that's a limitation of this instrument. It's a limitation of its compact size and its inexpensive structure. So let's go ahead and take a much closer look at that and see how bad are these tones. Are they going to limit the measurements? How can you get around them? Is there any way to limit their interference with your signal? I've done some study on that, which is pretty interesting. So let's go ahead and take a look at that. So the unit is connected with a USB 3.0 cable, which is provided, of course, when you purchase this to the machine itself. I'm going to here use my Surface 3, and I'm going to just record the screen because I like to go back and forth between the setup and the screen, and this way we're going to be able to do that. So let's go ahead and launch Signal View. And here on my Surface, I've installed the free version of Signal View, as I mentioned, with all the measurements that are coming for free with the price changes from Tektronix. So I don't have all the fancy demodulation licenses on this. All those are my licenses are on my desktop. So when we're going to do those experiments, we have to take a look at my desktop computer. But this is a good representation of what you can expect when you get this unit. So let's go ahead and go under Live Link and connect to it. So you can see it shows up here as a USB instrument that's connected to the computer. It's going to take a few seconds for it to establish a connection, and the LED that's in the front of this unit right now, which you cannot see, this LED in here blinks, red and green, and once the connection is established, there it is, you can see it. There we go. Here we go. So the instrument boots up in this preset window. I can go ahead and just click on preset. Doesn't really make any difference. So it starts off at having a center frequency of 1 gigahertz with a 40 megahertz bandwidth. You can see how fast the spectrum is changing. That's because it's doing really, really rapid spectrum reporting. So far it looks good. Let's go ahead and show all the settings. And this thing, by the way, is actually somewhat touch friendly, because you can go ahead under View and tell it to show the numeric pad. I'm not going to do that because I don't want to keep bringing my finger in front of the screen and block your view to enter the values. So I'm just going to use the mouse and the keyboard. But in the field, you don't need that. You can just use the floating touch pads that jump up and that appear and disappear as you try to interact with the software. So far we're going to go ahead here and go maximum span. There it is. So under maximum span, we are going from 9 kilohertz to 6.2 gigahertz, and you can see that it will sweep much slower because it is changing the internal LO frequency along. Of course, it's sweeping just like a spectrum analyzer is, and it's capturing 40 megahertz windows, and it's doing the analysis and so on and displaying. And the bottom left here, it's telling you, acquiring, stopping, and so on and on. So it's telling you the interface that it is doing to the instrument itself. So let's go ahead and change the resolution bandwidth from 1 megahertz to 1 kilohertz, so 1,000 times smaller, and look what happens. So far so good, but then, these are the tones they're talking about. These tones here is what is limiting their spurious-free dynamic range, because they're measuring their dynamic range, their spurious-free dynamic range with respect to the peak of these tones. In fact, let's go ahead and go under marker, and let's look at the peak. The first peak is at DC, of course, 9 kilohertz, but that's nothing. That has nothing to do with the spectrum analysis. That's common. So we go forward, there it is. So this peak is sitting at 914 megahertz, and look, it's at minus 55 dBm. This means that from the 0 dBm mark, you have 55 dBm before you see that first tone. But that's really annoying, because I don't know why they couldn't completely get rid of these tones. I haven't taken this apart. Maybe I'll do so in a different video, because I'm curious to see what's inside it. So maybe we'll do a teardown later. But they couldn't get rid of this. This to me looks like perhaps an LO leakage or some kind of a coupling between the LO that's sweeping internally and it's still getting digitized coming out of the IF port, and maybe because of the size of the instrument they couldn't get rid of it. So how big of a problem is something like this? Well, the very first thing I should tell you is that all of these tones actually aren't present at the same time. These tones appear within a particular window that you're looking at the signal, and I'll show you that in just a second. So for example, this tone is sitting at 914 megahertz. The next tone is sitting at 1.08 gigahertz. So you would expect that if I look from 900 to 1.1 gigahertz, I would see both of these tones. Let's go ahead and verify that. So if I start at 900 megahertz and stop at 1.1 gigahertz, look, those tones actually aren't there anymore. Only one of those two tones there, and if I go and look at the peak again, there it is. Only the tone at 1.08 gigahertz is now present. The reason is because these tones are LO tones, so they're only there within the span, within the frequency span that you're looking at. So the problem isn't actually as bad as it seems. If I go full maximum span, you can see this tone right here at 1.08. Now if I go maximum span, you're going to see the other tone, but as you just saw, zooming into this region, that tone wasn't there. That tone is going to show up only if you're looking at this part of the spectrum. So the problem isn't as bad as it may seem. But on full scale, it looks pretty annoying. So let's go ahead and inject a signal of our own into the spectrum and see what happens. In order to inject a tone into the signal, we can't just go ahead and straightforwardly inject a tone. And the reason is because these units aren't designed to have a THC that's very good. We don't want to be limited by the total harmonic distortion of the unit itself. So what I've done is that I have taken the output, you can't see very well, but I've taken the output of the synthesizer, connected to a microwave filter, and then I've taken the output of the microwave filter and then fed it back onto the instrument itself. And right now the microwave filter, I've set it to 1 gigahertz. So this is the lowest that this particular model goes to that I have. So this allows us to inject a 1 gigahertz tone, which is actually good because a 1 gigahertz tone happens to be exactly in between these two tones that you see on the screen. So we can capture the interaction of that tone with all the other tones and see if they're actually interacting. So here we go. I've set the instrument to 1 gigahertz here at 0 dBm. That will bring us to the full scale at the very top of the software here that is shown as 0 dBm. So here we go. So let's go ahead and try that. So I'm waiting. Where is it spanning at? I think it's, where is the sweep right now? There it is. So it's sweeping right here. Oh, we just missed it. So hold on. I'm going to wait until it goes around. Here we go. I'm enabling the output. So now you're going to be able to see. Look at that. First of all, you see that extra tone that wasn't there. So that extra tone that is showing up here is the interaction of our tone with some of these other tones that are around that region. So again, this is because of the mixing products of the internally non so well isolated tones that are inside and the tone that we just injected. So this is the full scale tone we have sitting at 0 dBm. If I go look at the peak, here you go, it says it's at 999.75 blah blah blah, and it's at 0.25 dBm. Okay, fine, that's what it should be, and the filter is doing a good job at getting rid of all the other harmonics. So let's go ahead now and take a closer look at this region. So let's look from, let's look at, this is at 705 megahertz and the highest tone is at 1.08. So let's look at start at 700 megahertz and stop at 1.1 gigahertz. There we go. There. So here we go. So it's a better view of what we were talking about. So here's that tone that we didn't want, that tone that I showed you before when we zoomed out that far. And I'm going to go ahead and disable signal. There we go. And that's the other tone. Again, I'm looking at a much wider region, and I remember I mentioned that if you look at the lower frequencies, you're going to see the other spurious tone. So here it is. This is a 940 megahertz tone. This is the other tone that was at 1.08. They're still both there. I'm going to enable my signal. And there it is. You can see some other spurious tones appearing. So yes, that's a problem, because right now, if I were to go ahead and reduce the amplitude of my signal, so I'm going to go ahead and reduce the signal amplitude. Let's go ahead low enough until this tone is as big as the other tones. There we go. So if you're faced with a situation like this, now we're at minus 55 dBm, which is the spurious free dynamic range of the instrument. Yeah, you can't see it. You don't know which of these is your signal. You can turn it off, and you can see that's the one that goes away, but the other two are going to be there. So that's a limitation at some of the frequency bands of the instrument itself. So if I go full scale now, you can see that my tone is going to show up right in the middle. You can see this, out of these three tones, only one of them is real. It's the one that I'm applying. But again, it's important to know that this problem exists only in some of the frequency ranges, and if you zoom far enough, you won't see it. So let's go ahead to a center of 1 gigahertz, and let's look at a span of 40 megahertz. There we go. Now this is the signal I'm applying. You can see that there is no other spurs within the 40 megahertz that I'm looking at. So I can go ahead and increase the signal, and look. There, this is 0 dBm. Now, here you're only seeing these two tones. These two tones are your spurious free dynamic range within this analysis window that you're looking at. This is now really, really good, because it means that your spurious free dynamic range, now you have an easily, like about more than 70 dB of spurious free dynamic range, which is perfect, not a big problem. So let's go back to that scenario that was bad, but there is a way around it. So here's that undesired scenario again. This situation where your tone, which is this one, the desired tone, is lost between the other two tones. But the really good thing is that these tones actually do not scale when the reference level is adjusted. So here we go. So this is our tone. Now the reference here is 0 dBm. So you have a much larger reference than the signal you're trying to measure. So there's no reason to have your reference at 0 dBm. Let's set our reference at minus 40 dBm. and look what happens. You see that? Now your signal is much stronger than these tones. These tones actually scaled directly with the reference level. Now I can forgive Tektronix for the fact that at least these tones don't stay at the same power when you change your reference. So if I go even lower, let's say I set my reference to minus 50 dBm, there you go. Now this is my signal of interest, and these are the spurs that I don't want. So here at least I can take my signal out of the noise, out of the undesired tones much easier, which is of course great. This is exactly what I wanted. Now if I go ahead and increase my signal, of course at some point it's going to now stick above the, you know, now there's the arrow says it's well above the reference, so you can't read it anymore, but you can read the exact amplitude. But you can see that under these settings, in order for my signal to be lost in the noise, I have to change its amplitude to minus 92 dBm. So now my signal is minus 92 dBm, and now it's again at the same amplitude at the spurs I don't want. So this is a limitation. I wanted to really show it to you guys because I wanted you to appreciate what you're dealing with and how to get around it. So if you go ahead and scale the peak amplitude, then you can reduce the spurs amplitude directly with that, and then your signal can stand out. So that's one way to get around that. So here's another instance. Again, here's our 1 GHz signal at full scale. So you can do other fancy things. You know, I can reduce the span to a much smaller value, 1 MHz. Now you can see the phase noise. This is a combination of the phase noise of the synthesizer and the phase noise of the spectrum analyzer. I can go ahead under traces and I can apply a particular averaging, and I can do a 64 times averaging, so you can now see really nicely what the curve looks like. All right. Well, enough of this single tone measurements. Let's go ahead and do some more fancy stuff. And to really strictly see the spurious-free dynamic range, for example, at 1 GHz here, I can go ahead and apply a two-tone signal. So I've set up the instrument to be able to do two tones. So I'm going to go ahead and turn the two-tone on, and you can see what happens to the spectrum. There you go. Now you have two tones being applied. I can go ahead and increase the amplitude so that the total amplitude is still at 0 dBm peak on each tone. There it is. You can see now this is the LO leakage of the instrument itself, not the spectrum analyzer, but the arbitrary waveform generator plus the synthesizer. So you can go ahead and look at this tone. You can see this sitting at again at minus 55. So under this two-tone condition, you have again a 55 dBm spurious-free dynamic range. So you have to keep that in mind to know the limitations of the instrument in order to be able to do your tests properly, not to get wrong results and not know where they're coming from. Again, I'm not 100% sure. It's difficult to isolate the third order intermodulation products to know whether they're coming from the synthesizer or they're coming from the instrument, but in this case it's a combination of both. But again, very impressive results. It's that this isolation issue, of course, is difficult to get rid of. I don't exactly know internally how the design was done, but anyhow, let's move on. So for the next couple of experiments, I'm going to use this little evaluation board. Normally I like to set up my own experiments, but this is a really impressive little board, and you can do quite a bit of interesting things, which allows us to evaluate the performance of the USB spectrum analyzer. So at the heart of this, there is a Spartan FPGA and an Atmel SoC and some memory. There's a couple of cages here which house either some sensitive RF or some DC-DC converters. Underneath them there's a little SD card for reading, I guess, various configurations or perhaps waveforms and so on. There's a bunch of analog circuitry around it. But what is really impressive is that this board can do INQ up conversion and down conversion and so on, all built together in the same little PCB. So you can do a whole bunch of really complex type of evaluation. There is not much on the other side of this board, and I can go through the detail of it, but this review is not about this board. But I'm going to use this to check a couple of the functionalities of the spectrum analyzer. You can see there's a whole bunch of LEDs here which you can select, which various different type of signals that come out of it, and there's a specification which each of these signals, and then you can use the spectrum analyzer to analyze and debug and find problems and so on. So I'm going to go ahead and connect the RF output to the spectrum analyzer. We're going to power this with a 5-volt supply. Usually you're supposed to power this with 2 USBs because it takes more than half an amp, but anyhow I've just gone ahead and connected to a regular power supply. So let's go ahead and connect it and see what we can do with it. So here's our setup. Nothing fancy going on. I've just connected the RF output of the evaluation board directly to the spectrum analyzer. You can see the LED blinking. It means it's communicating with the computer. So it's sitting right here and with the cable connected so on. And I powered this on, and it's on a continuous wave. It's just generating a CW waveform. So let's go ahead and take a look at that. And I just wanted to point one thing out, that I mentioned that the phase noise of the instrument is minus 85 dBc per hertz at 100 kilohertz offset. That's at the worst case, that's at 6 gigahertz. At 1 gigahertz is about minus 92 dBc per hertz at 100 kilohertz offset, and that's, you know, makes sense that there's about a 6 dB difference. That's because they're internally doubling the LO between 3 and 6 gigahertz, and that's how typically spectrum analyzers are done, as we've seen in the past. So let's go ahead and take a look at this signal. I've already preset this, you know, I made the mouse a little bit bigger so you can see it. The center frequency is at 2.445312. It's right around the Wi-Fi region, so it's good that they, you know, we're doing this test at a region which will be of most interest to most people who are working around these frequencies. So there you go, we can see our waveform. Nothing fancy, but we can go ahead and measure its phase noise. I just wanted to show you how to do that really quickly. We're going to go ahead and change the resolution bandwidth. Let's say, actually, let's change the span to 5 megahertz, and go ahead and change the resolution bandwidth to 1 kilohertz. And you can see now the shape of the noise a little bit better. And I can go ahead and add a marker to the peak. There it is. Now it's giving me the peak value at minus 5 dBm. I can go ahead and add another marker. Now it's a reference marker, so it's going to be with reference to this peak at the top, and it's telling me what offset I want. Let's put it at an offset of 100 kilohertz if I want to measure the phase noise at 100 kilohertz offset. And then under define, I can tell it give me a dBc per hertz delta readout, and it's going to do some averaging because it has to, and then it's going to tell me that the delta M is about minus 86 dBc per hertz. So it's pretty close to somewhere in between the phase noise of the unit and the phase noise of the board, but you can see the shape of the PLL response of the evaluation board, and we saw the shape of this with my external synthesizer, and it didn't look like that. So this shape of this synthesizer is definitely the PLL response of the PCB. So you're going a very quick and easy way of getting phase noise measurements from this, pretty straightforward. So I'm going to go ahead and switch this to the functionality of the CW pulse. Now, I'm sorry, the infinite hop. So the hopping signal is going to be a particular frequency shift every 1.28 seconds. So every 1.28 seconds is going to jump from 2.445 gigahertz to 2.458 gigahertz. So it's going to do this jump. So let's go ahead and switch that to the other function and go ahead and take a look at it here. So now you don't really see anything yet, but occasionally this is actually jumping. So in order to see that much better, we're going to go ahead and enable the DPX, which is one of the main strengths of this instrument. There we go. And under DPX, you can already see some tone appearing and disappearing, and it's capturing that. So let's go ahead and make this a split. So now not only we have the DPX itself, we also have a running spectrum up here, spectrograph right up there. So let's go ahead and change some settings in here. Let's go ahead and change this to minus 80, just so that, oops, minus 80, so that we can have a little bit of a more clear view. And then let's put this to 1, and let's set this to 3%. There we go. Nice and easy. Now you can see it much better. So now you can see every once in a while that indeed we are catching some frequency shift that appears and disappears, and it is catching this at a particular interval. Now we want to make sure that the repetition rate in which it is catching this spurious tones is actually matching what is coming out, because it is supposed to catch every single one of those, because it's supposed to have 100% probability of intercept for this pulse that's 100 microsecond in duration. So if I go ahead under preferences, I can actually tell it to show the readout, and look, it says 100% probability of intercept at 100 microsecond. Is that true? Well, let's go ahead and pause this for a moment, and let's go in here and let's go ahead and add a marker. There we go. I can put that marker. Look, as I move this marker up and down, you can actually see the particular specific spectrum that was captured. Look, every time I go through these little points that are here that show the jump in the spectrum, I can actually see the individual waveform appearing, which is a really powerful idea. There we go. So I can put this one right here, and I can go ahead and add another marker, and I can put that marker right there, and this guy right there. There we go. Look at that. About 1.3 seconds the difference between two. It's very hard for me to place them with the mouse with the camera in front of me, but there it is. Look at that. A 1.3 second interval. It is capturing. It's supposed to be 1.28 because I can't place it perfectly, but you can see that it is indeed intercepting every single one of those points. And I can go ahead and zoom a little bit closer just to make sure you really see it. There it is. You can see these individual little traces on the spectrograph where this spurious tone appears and disappears. So you can see why this is such a powerful idea, because if you are working in a field and some spurious tone comes and goes and you don't know where it is coming from, you want to be able to have a very, very high probability of capturing that, even if the tone is very short. Remember, this is 100%. This tells you the repetition rate, the exact repetition rate of this tone. That's not necessarily what you might be looking for. If you just want to see if something's appearing or not appearing, if you don't want to catch all of it, the tone can be even shorter than that, which is important to note. This is 100% capture of every single one of those tones. So I've gone ahead and maximized it so you can see it better, but now you can see that still the interfering tone come and go. But what if this tone wasn't as frequent as 1.28 seconds intervals? What if it was something that happened, once every 5 hours? You don't want to sit there and look at this, so you want to be able to define a test where you can capture this and then have an action that happens once this violation takes place. Maybe save an image or save the waveform, or do something to let you know that this happened. So that's really easy to do actually, because you can go ahead and define a mask for this. Again, all of these, every feature that I'm showing you is free in Signal View when you purchase the spectrum analyzer. There's all the things that Tektronix has made available for free. So let's go ahead under Tools and go Mask Test. So when you bring up the mask test, oops, I think I just closed it actually, there it is, mask test menu down here, you can go ahead and say that where you want to apply the mask to. I want to apply it on the trace, which is this trace that I'm looking at, and I want it, there's a bunch of different kind of masks you can apply, but how about one that's outside? So if anything is outside of this region of interest, we can trigger on. So I can go ahead and edit the limits, and then it brings this this little window for me. Let's make it a little bit larger. There it is. Actually, it's really nice because this window is showing me the live spectrum. And let's go ahead and pause this for a second so it doesn't interfere with us. There we go. And I can go ahead and actually drag these points around and define my own mask. It's kind of fun. There we go. We can define a mask like that, and we can add a point, add a point here, add another point here, and then we can go ahead and move these points up and so on. And you can go ahead and define any kind of mask you want. Or because this waveform shape is known, we can go and say auto draw. And look, it does a little mask for us based on this waveform. It's kind of guessing that you were interested in this portion, so I'm going to draw this for you. Beautiful. So that's done. We can go ahead and say done, and I'm going to go ahead and run this again. There we go. So it's running again. So now I can go ahead and actually enable the test. If I go to enable, there it is. It draws something around my waveform. This is the mask I just defined. Look at it. And every time it crosses this, you can see that it marks it as a violation. But what can you do? Well, you can take a whole different kind of actions, up to 5 actions at a time when the mask is violated. You can save the picture. It can also tell you, it can also say how many files to save, up to maybe a maximum of 100, but it can put more, of course. It's only limited by a storage space. And then you can tell it to do different things. How about telling it to beep every time that the mask is violated? There we go. You see? You can hear that. Now, the beep is useful if you're working in the lab, you have your ear on this, and every time something happens, and what else you can do, you can also say stop the acquisition if it happens. There you go. So it happened, it stopped the acquisition. You can see the trace left over here, and then you can go ahead and put a marker and look at it on the spectrograph. So it's really, really easy and really, really straightforward to set different kinds of masks, which is very powerful. And this being able to intercept something with 100% probability is an extremely useful tool. So let's take a quick look at some FM modulation, which would be a little bit interesting before we move on to doing some actual complex constellation demodulation using the licensed version of Signal View. Let's go ahead to, there you go, let's do an FM modulation. Now if I go ahead and look at the tone on the spectrum analyzer screen, you can see that it's kind of wiggling around a little bit. That's because it's obviously FM modulated. But let's go ahead and see if we can demodulate this. Very first thing we can do is go ahead under this window. Again, you can see that these are all the free analysis that you can have, and I suggest you go ahead and play with these because there's so much you can do. I can spend hours talking about each of these. I just want to give you an overview. Let's go ahead and add an FM modulation, and go ahead under Signal and add a DPX. You can see how easy it is to add something particular to this, and go ahead and say OK. There we go. So here's our, well, obviously it's not set up yet, so here's our demodulation, here's our DPX view. Let's go ahead and change the span of the DPX to 500 kilohertz. There we go. Aha, look at that. A classic FM modulation shape, and because of the extremely high sample rate, the waveform update rate, you can actually capture the whole thing. Pretty amazing with the color coding and everything. So let's go ahead under FM modulation. First, let's go and change the analysis length. Remember, if you're doing FM and AM modulation, you have to capture enough signal for the demodulation to actually mean anything. So let's say we want 10 milliseconds. There we go. And now you can see on the right side that we have we're not able to demodulate the entire width of the signal because our analysis time is incorrect, and we can go ahead and fix that by saying that the measurement bandwidth should be larger, let's say 200 kilohertz. There we go. Here we go. So there it is. So now you're actually reading out, I can even auto scale, I think it's already auto scale. So it's telling me that the plus peak is at 100 kilohertz, negative peak 100, plus peak at 100. So peak to peak 200 kilohertz. So this is an FM signal centered at 2.445312 gigahertz with an FM modulation depth of 200 kilohertz, which is exactly what it is supposed to be. So you can see how quickly you can set up various modulation type, and again this is a 10 millisecond scale, so the modulation rate itself is about a kilohertz. Again, everything is beautifully captured, easy to see, and because of the DPX technology, you can also see the color grading and do really quick and easy demodulation. So I've gone ahead and connected an antenna to this. Let's see if we can catch some FM radios to actually listen to it. Since I showed you some FM demodulation, I thought it would be fun to try and capture an actual radio station. So let's go ahead and look at the radio station and let's find one that has a pretty strong signal that we can actually listen to. Let's go to 97.5 megahertz, which is, you know, let's say pick a center there, and let's look at the span of about 20 megahertz, and let's change the reference to minus, let's say, 50 dBm. There we go. As you know, I can see a few different stations. Again, this antenna that I have is not suited for this frequency range, but nonetheless, we can still pick something. So here's one. Let's go ahead and say marker to peak. There we go. We can go to peak frequency, and maybe I can bring that to the center. Let's go ahead and change the span to 500 kilohertz. There you go. So you can see it looks like a mess because it's an FM modulated signal right now. Let's go ahead and again add our FM demodulation window. There we go, like so. Let's change an analysis time to the 10 millisecond we had before. There we go, we're starting to see something, and we can actually go under audio and run it. There we go. You see? I don't know if you can hear it or not, but there it is. That's one station that I just randomly picked. I don't know what station this is, but there you go. Works pretty well. Demodulation, really easy to do. So for the next experiment, I've actually moved to the desktop because I want to show you some of the more advanced features. So let's take a quick look and see what I have here. So I've connected the spectrum analyzer to my Anritsu programmable attenuator, and the reason I'm doing that is because I'm interested in being able to change this input signal power close by because the synthesizer is quite far away, and that way I can change the attenuation level and we can find out the sensitivity and the noise floor of this instrument, see if we can demodulate complex constellation with very low input power, which is very important, especially in field use. So here we go. So then the input to the signal just, you know, it's just routed on the table, and then it goes all the way to my synthesizer, and on the synthesizer itself I am going to set up, I have already done so, I've set up a custom waveform, which is a QAM constellation. This is a 256 QAM with a root raised cosine 0.35 filter applied to it, and you know, everything else is pretty straightforward. It's going to be centered at 2.5 gigahertz, and it's enabled and is running right now. So, and the output power is 0 dB. I'm going to keep that there, and we're going to follow this back, and we're going to put the camera back here like so. There we go. We can go ahead and look at the screen. There it is. So what I have here, I'm basically running signal view again, except on the desktop, and here I have all the licenses that are available from this software, all of them at the same time, and that's the reason why I moved here, so we can actually take a look. So let's go ahead and set the center frequency to 2.5 gigahertz. There we go, like so. So now you can see the waveform here, and this is a typical QAM constellation spectrum here, centered at 2.5 gigahertz. I can go ahead and, for example, change the resolution bandwidth to, let's say, 1 kilohertz, for example, like so. There it is. So you can see it really nicely. You can see the out of band signal. It has very low distortion. I cannot increase the signal amplitude more than this because my synthesizer is not linear enough, whereas this has no problem, of course, to be able to receive that signal. So let's go ahead and do some basic things. Let's add a whole bunch of different analysis types. So let me zoom in here so you can appreciate all the things we can do. So let's go ahead and add a DPX. From this, nothing else from here. Let's go under digital demodulation. This is again a paid license. This would be $990 after price reduction, which is a really good deal. Constellation. Let's look at the signal quality. Let's look at the eye diagrams and the demodulate I and Q versus time. That's about that. In the RF measurements, let's look at channel power and adjacent channel power ratio. Let's look at the occupied bandwidth, which is a useful thing to look at. And it's good enough for now. Let's go ahead. Let me see if there's anything else that I want. Not pulsed RF. Again, I'll just give you what you can do all kind of wireless LAN analysis, audio analysis. You can do complete audio analysis. P25 is a whole suite for that. Pulse RF, OFDM. There's no limit on what you can do with this software. But I think for the purposes of this initial test, I think we are good. There was one other thing I wanted to do, and that was EVM versus time. There we go. There you go. Now it's going to go crazy. It's going to add all of these windows for us at the same time. So let's go ahead and run this. There we go. So we have to start setting this up. So let's do one at a time. Very first thing to notice is that we are able to read over here. I hope that you can see this. This is now telling us that the occupied bandwidth of the signal is about 6 megahertz or so. That's 99% of the power is contained within that, and you can see that it's automatically adjusting, and it's telling us that the occupied bandwidth has about -4 dBm of total power in it, which is very useful. So this makes sense because the symbol rate of our QAM constellation is actually 5 megasymbols per second, and because we're using a root raised cosine alpha factor of 0.35, this bandwidth occupation actually makes perfect sense. So that's great. So let's go ahead and go down one here, and let's go ahead and set up our power measurement for our channel and our adjacent channel. So we know that our channel is going to be, let's just allow the channel to occupy a 7.5 megahertz bandwidth, and let's say the channel spacings are 10 megahertz apart. There we go. So now it's setting up this measurement for us. It's telling you that, look, your out of channel on the left is -55 dB, channel on the right is -56 dB with respect to the total power in the main channel, which is about -4 dBm. So this is a very useful measurement because if you had, for example, interferences or if you had nonlinearities, then you could tell how much power you're occupying in an adjacent channel. I'm going to show you that. So I'm going to go ahead to the synthesizer and I'm going to increase the signal power until these intermodulation products out of band start to creep up, and then you can see this number change. So here we go. I'm going to increase the power. You see? There it is. Oh, that's too much. There we go. So here now you can see that the spectrum has significantly changed, and you can see that you have this is actually, this channel spacing is not really counting that. So let me go ahead and make this as 8 megahertz, make this narrower. There it is. So you can now see that we've lost significant out of channel power ratio because of that, and I'm really close to overloading actually the spectrum analyzer itself. But you can see that something like this can be used to measure the interference outside of the channel. There we go. Turn it back to 0, and you can see the number improves again. So that's for that one. Let's go ahead and set up our demodulation. Actually, there you go. So let's go ahead and click here, and I'm going to go under settings. There we go. Sorry about the camera. I hope that you can see what I'm doing here. There it is. So you have quite a bit of options on demodulation. This thing can this software can demodulate all these different type of modulated signals. So 256 QAM is actually the highest, and we know that the symbol rate is 5 mega symbols per second. We've already determined that, and the filtering is 0.35. Beautiful. And I think everything else we can leave to automatic. We can change the analysis time to look at 2048 symbols, and I'm asking it to do that because I want to make sure that we capture sufficient amount of data in order to create a reasonable, good-looking constellation. So there it is. We've done that. All of that is good and nice, and look at that. There's the constellation. Look how beautiful it is. Well, we'll find out if it's beautiful or not. It's actually not that great, but that's not the fault of the instrument. It's actually from the synthesizer itself. So let me go ahead and remove the trajectory traces from this. We're only going to look at the points. There. So here's constellation. So you can see that it's okay. It's reasonably a good constellation. Its EVM is about 6 to 7%. And I think one of the reasons its performance is poor is because of the fact that I'm putting out quite a bit of power from the synthesizer. You can see the corners sometimes get curved up. And there is one other reason why this is not as good as it should be. And this is something that most people don't pay quite attention to. Let's think about how the software actually does this demodulation. So it has a center frequency. Then it captures the spectrum, and then I have told it, the only thing it doesn't know is that I have said to it what the symbol rate is. So it's going to assume a particular symbol rate, a particular symbol repetition rate in between each of these. And you can see that if I look here, this is the eye diagram of the I and Q signals. You can see tiny dots in the middle. Those are the eye diagrams. And up here, you can see the demodulated signals. So this, remember, this is 256 QAM, so there is a whole bunch of levels. What would that be? That would be 16 times 16. So it would be 16 levels on I and 16 levels on Q. So you can see that it's demodulating all of those. But remember that every time it jumps from one symbol to another symbol, it has to assume that the repetition rate is 1/5 megahertz. But because it is using its own internal reference, which is not the same as the internal reference as the synthesizer, it's going to drift over time. And that explains partially why the constellation is not as good as it could be. And here you can see the EVM versus time, so you can see how the EVM changes versus time, and sometimes you see these big peaks, and I believe this is due to the fact that there's a drift over time. So if I go ahead and change the analysis time to a shorter amount, let's say 1024 symbols only, you can see that we have nice looking constellation. Sometimes it's missing a point because there's not enough points for it to catch. But all of this analysis, if you saw, took me only about 10 seconds to set up, and you can get a tremendous amount of information from it. Here at the top I can see that the EVM of the constellation is about 2%, which is pretty good, which is about -33 dB. It gives you a whole bunch of other IQ offsets and errors and peak deviations and so on, which is pretty good. I was reading a peak EVM down here before. The RMS is about 2%, which is actually as good as the source can do. So there's a lot of different type of analysis that you can do really easily with this software. So now we can go ahead and change the attenuation as I described earlier over here on this guy. So I can go ahead and continue to change the attenuation, and then let's see what happens to the constellation, and at what point will the instrument basically not be able to capture the constellation anymore because we will be below its own signal to noise ratio. So let's go ahead. This is 0 dB. There you go. I just changed it to 10 dBm. So now there's a 10 dB attenuation. You can see that the total reported power now went to -15 dBm. It used to be 5 dBm. So let's go ahead and keep changing that. 20, 30. Now it's the 30 dBm. So now you can begin to see that it's running into some problem. So let's go ahead and change the reference value, of course, because the reference is still set to 0 dBm. So now you're capturing a -35 dBm total power when the dynamic range is huge. So let's go ahead and change it from 0 dBm, let's go to -20. There we go. Of course, then as soon as you do that, the attenuation, the noise figure of the instrument now has improved by 20 dB because I removed 20 dB of attenuation from. So now it gets much better again. So let's go ahead and continue to reduce it again. Now this is -40. Now this is 50 dBm. Once again, we're running into the noise floor. Let's go ahead and change the reference to -50. There we go. Back to regular analysis again. Remember, I improved the noise figure by a tremendous amount. And here we look at that. You can see that now the total received power is only -55 dBm. So we're demodulating a 256 QAM signal with a total received power is only -55 dBm. That's pretty amazing for an instrument, for a USB-based spectrum analyzer. That's pretty good. We can go ahead and add more. This is oh, hold on, I messed up. This is now 60. Still not really any problem. Let me go ahead and change this to -60. At some point we're going to run into the noise floor. So it is now pretty much at the edge of what it can do. Let me see what happens if I go -70. There we go. So let me go ahead and increase the attenuation to 70 now. There we go. Now no, it cannot really demodulate 70. This is as good as it's going to get. Let me go 65 dB attenuation. It's beginning to start to demodulate, but it's having a hard time to do it. You can see sometimes it loses the lock, but it's reasonably good. So let's try at 60 where it was working. There we go. So it has absolutely no problem demodulating. Now it's reporting an RMS EVM of about 4% now. Now you can see that it's definitely limited by the instrument itself. But keep in mind, this is a -65 dBm total power, 256 QAM signal that is trying to demodulate. If I go ahead and change the constellation to a different type of constellation, we can go even lower. We can even demodulate lower because you don't need as much signal to noise ratio for a simple constellation. So this is 256 QAM. Let's go ahead and try something less complex and see what we can do after that. There we go. I changed the modulation to 32 QAM. The power is still the same. The total received power is still only -65 dBm. But again, it has absolutely no problem demodulating now. Now we can easily demodulate 32 QAM. I can go ahead and increase the attenuation even more. Now it's 70 dB. There we go. Now the total received power is -75 dBm, and it can still do a demodulation without any problems. I can yet again scale back the constellation to even a simple constellation in order to be able to add even more attenuation. So here we go. I'm going to change it to a very basic 16 QAM signal now. There it is. There's our 16 QAM signal. So let me tell it that this is indeed a 16 QAM signal. And voila. There we go. Look at that. No problem. It can do easily demodulation of the 16 QAM. You can see the eye diagrams right here with a received power of -75 dBm. I can go ahead and make it maybe even a little bit harder. Now it's really pushing it because it is really close to the noise floor. Now you can see how close to the noise floor we are because the total received power is -80 dBm. It's a tiny signal, and we can still demodulate it. And you can see occasionally it loses the lock. So it's going to have some bit error rate associated with it. But again, no problem. This really is a very difficult test for any instrument, and it can do this because of its large dynamic range within this analysis window, along with all the other capabilities that we saw. Well, I hope that you enjoyed this world exclusive introduction and review of the Tektronix RSA306. It's a very capable unit, and now that I understand some of its limitations and how to work around them, I can really get the most out of it. Especially when coupled with the free signal view that is a really capable software. As you saw, you can do a tremendous amount of different kind of measurements in it that's now either significantly reduced in price for some of its functions or is totally free. This makes this a really attractive solution, and I really think that every university should have one of these on their benches for their laboratories, because there's always an oscilloscope on the bench, and this allows the students to learn how to think in the time domain and what signals look like in the time domain, but rarely do they ever really learn how signals look like in the frequency domain. This allows them to think in both of them and look at the duality between the two domains. And because it's so inexpensive, and because it can be just placed on the bench and barely takes any space, it burns no power, doesn't require an external power supply, it's rugged, for students that's really important, and this will allow them to create some really nice RF labs and have the students to have even more experience before they graduate. So I hope you really liked this and enjoyed the review. There's so much more I can do with this, and I will have other videos about it. I might even take it apart so we can take a look at what's inside it. But if you like this video and my other videos, as always, I always only ask for one thing. Just go on the website or go on the YouTube channel, leave a comment, like it if you do. And if you're going to purchase something like this from Tektronix, and if you do so because you saw this video and you liked it, let them know that this is what happened, because it allows me to have a good relationship with them and continue to bring to you really, unique and interesting reviews of different products, and always be at the edge of all the things that are released on the market. So just spend a few seconds and go ahead and do that. I would appreciate it, and until next time.